In this video, we're going to look at collisions in one dimension. That is, we're going to look at collisions where two objects come together, collide, and bounce off of each other along a single line. They don't move off this way or this way. They just bounce off each other, or they can stick together along one straight line. So we can describe this whole collision by using velocities and momenta that exist along a one-dimensional line. So every collision, we showed that momentum is conserved. So P1 initial plus P2 initial equals P1 final plus P2 final. I can write this all out as M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Since this collision is happening in one dimension, I don't have to worry about the fact that these are vector quantities. I'm just looking at, say, the x component of the momentum, because that's the only component that exists. Okay, we're going to break collisions up into three types. There are elastic collisions. And in an elastic collision, kinetic energy is also conserved. So the kinetic energy of particle 1 plus the kinetic energy of particle 2, that is the total kinetic energy of the system, is the same initially as it is finally. It is the same before the collision as it is after the collision. So this is a special case, and most collisions are actually not elastic. It's kind of hard to make an elastic collision. In most collisions, kinetic energy is not conserved. Some kinetic energy is lost. And this kinetic energy can go various places. It can go to squishing the objects that collide together a little bit. It can be dissipated as heat. It can be dissipated as sound. It can be stored in a magnetic field. There are all kinds of places that kinetic energy can go. But usually in most collisions, there is some loss of kinetic energy during the collision. So in general, most collisions are going to be inelastic collisions, where kinetic energy is not conserved. And there's a special kind of inelastic collision called a completely inelastic collision, where the objects stick together. Two masses collide and stick together. This is the most inelastic type of collision. We call it completely inelastic or perfectly inelastic. And here we end up getting a really nice simple result for the final velocity of the two objects. Okay, so I'm going to go through I'm going to go through this special case of elastic collisions, and then I'm going to go through this special case of completely inelastic collisions. First, let's look at elastic collisions. We have two masses, M1 and M2. They have initial velocities, they collide, and then after they collide, they have final velocities. And importantly, all of these velocities are along a straight line. This is all happening along one dimension. These velocities aren't pointing up or down, they're just pointing either left or right. Okay, so we can say that momentum and kinetic energy are both conserved in this collision if it is in fact an elastic collision. So momentum conservation looks like M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And energy conservation, well, it's written on this slide. I'm going to just get rid of all those 1/2s. The 1/2 and the 1/2 mv squared just cancels out. So I can write this as M1 V1 initial squared plus M2 V2 initial squared equals M1 V1 final squared plus M2 V2 final squared. So this is momentum conservation, and this is energy conservation. Okay, so what I'm going to do is do a little bit of algebra here to rearrange these and get a nice result that allows us to calculate the final velocities in the case of an elastic collision. So first of all, I'm going to rewrite both of these equations, get all the M1 stuff on one side and all the M2 stuff on the other side. So for momentum, I have M1 V1 initial minus M1 V1 final equals M2 V2 final minus m2 v2 initial. Well, I can take this and I can factor the m1s out of the left side and the m2s out of the right side. So I get m1 times v1 initial minus v1 final equals m2 times v2 final minus v2 initial. I can do the same thing with my energy equation, and I get an equation that looks like this. m1 v1 initial squared minus v1 final squared equals m2 times v2 final squared minus v2 initial squared. Okay, so remember, these are differences of two squareds. I can factor those. So what I get is, well, momentum equation is still m1 v1 initial minus v1 final. This equals m2 v2 final minus v2 initial. And for energy, I can write this as m1 times the difference of two squares factors as v1 initial plus v1 final times v1 initial minus v1 final. And this equals m2 times v2 final plus v2 initial times v2 final minus v2 initial. Okay, now what I'm going to do, my favorite trick, I'm going to divide these two equations by each other. When I do this, look what happens. m1 cancels out. m2 cancels out. v1 initial minus v1 final cancels out. v2 final minus v2 initial cancels out. And this all becomes v1 initial plus v1 final equals v2 initial plus v2 final. So this is a special equation that I get if I have an elastic collision. That is, in any collision where no kinetic energy is lost, I know that the sum of the initial and final velocities for mass 1 is equal to the sum of the initial and final velocities for mass 2. But this only works in one dimension. In 2 or 3 dimensions, this formula falls apart. It doesn't work anymore. So this is my special result for elastic collisions in one dimension. v1 final plus v1 initial equals v2 final plus v2 initial. Now, I want to look at one special case of elastic collisions in one dimension. Let's say that we have two objects that collide elastically and their masses are the same. So if m1 equals m2, well then when I write out conservation of momentum, I get m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Well, all these m's just divide out. They're all the same, so I can divide through by m, and I get v1 initial plus v2 initial equals v1 final plus v2 final. Okay, now I also have this special equation I wrote up here, v1 final plus v1 initial equals v2 final plus v2 initial. And I'm going to once again do my favorite trick. I'm going to subtract these two equations. When I do this, well, v1 initial subtracts out on this side, and on this side I find that v2 final subtracts out. So I get v2 initial minus v1 final equals v1 final minus v2 initial. If I solve this for v1 final, for example, I find that v1 final equals v2 initial. So this tells me that when my masses are the same and I have an elastic collision in one dimension, the final velocity of mass 1 is just the initial velocity of mass 2. And I can plug this back into my momentum equation, and I'll find that V2 final equals V1 initial. Just a little bit of algebra gets me to that. So what this tells me is that the velocities of these two masses just trade off when they collide. If I have two equal masses colliding in one dimension, their velocities exchange. V2 initial goes to V1 final. So this velocity, V2 initial, the initial velocity of mass 2, becomes the final velocity of mass 1. And the initial velocity of mass 1 becomes the final velocity of mass 2. They just switch off. And you'll explore this phenomenon in your lab, your virtual lab that you're going to do on conservation of momentum. The other case I want to look at is the completely inelastic collision. This is where my two masses, M1 and M2, collide and stick together. So after the collision, they form a single mass, M1 plus M2, with a single velocity V final. So to solve for what this V final is, all we need is conservation of momentum. We know that M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. But V1 final and V2 final are both the same. V final equals V1 final equals V2 final. So on this side, I can write this as M1 V final plus M2 V final, which is the same thing as M1 plus M2 V final. I can just factor out M1 plus M2. So on the left side here, I have M1 V1 initial plus M2 V2 initial. And I can solve this for V final, and I find that V final equals M1 V1 initial plus M2 V2 initial over M1 plus M2. So on the top here, this is just the initial momentum of the system, initial P. And on the bottom here, this is just the total mass of the system. So to find the final velocity of these two masses after they've stuck together, I just divide the initial momentum of the system by the total mass of the system to find this V final. So it's very easy to find the final velocity when you're dealing with a completely inelastic collision where the two objects stick together. And in the case of an inelastic collision, where kinetic energy is not conserved but they don't stick together, this is sort of in between elastic and completely inelastic, well, then the only thing you can say is that momentum is conserved, and you oftentimes, in order to solve these problems, you need to know one of the final velocities in order to find the other one. Let's do an example of a perfectly inelastic collision first. These ones are easier. So a piece of putty with horizontal velocity V initial equals 20 meters per second and mass MP equals 30 grams impacts a block with a mass MB equals 270 grams, which initially is at rest on a frictionless surface. If the putty sticks to the block, what is the final velocity of the system, and what is the energy lost in the collision? Okay, so first of all, let's just go ahead. We'll define a little coordinate system here for this system. This will be X, that's Y, and all the action here is happening in the X direction. The initial velocity of the little piece of putty, V naught, is just going to equal 20 meters per second in the I hat direction. Okay, so this piece of putty comes in, it hits this block, and it sticks to it. So you can imagine after the collision there's a little lump of putty here on the block, and the whole system is going to move in the same direction with some velocity V final. And we know V final is also going to be in the X direction. So we'll say something like V final equals just the magnitude of V final times I hat. Okay, so part A, we want to find the final velocity of the system. Well, we can do this using conservation of momentum. That is, we know P initial of the putty, so I'll say P initial, plus P block initial. This equals the final momentum of the block plus putty. So this is P putty final plus P block final. Okay. So first of all, we know the initial momentum of the block is 0. Block is initially at rest. The initial momentum of the putty is just going to be the mass of the putty, MP, times V initial. This equals the mass of the putty times V final, plus the mass of the block times V final. Importantly, these V final here are the same as this V final here. Both the putty and the block have the same final velocity. So I can solve this equation really easily. I just get V final, well, let's do this. I have MP V initial equals MP plus MB times V final. I can solve this for V final. I get V final equals MP V initial over MP plus MB. If I solve that for V final. Well, now I can just plug in my numbers. This equals, well, MP is 30 grams, and I'll just write it like this. This is 30 grams over 30 grams plus 270 grams. And then this whole thing is multiplied by V initial, which is 20 meters per second I hat. Okay? So if I plug all this into my calculator, I just get 30 grams over 300 grams, which is 1 over 10. The grams cancel out, the units don't matter, times 20 meters per second I hat, which of course is just 2 meters per second I hat. So after the putty hits the block and they stick together, this whole thing slides to the right with the final velocity, V final equals 2 meters per second I hat. Okay, that's pretty easy. All we had to use here was conservation of momentum. We didn't have to worry about energy. We didn't have to worry about anything except for saying that the momentum of the system was conserved. That allowed us to figure out how fast the block plus putty slide across the table after they stick together. So we found V final, the final velocity of the putty and the block after they stick together and start sliding across the table. They slide across the table at 2 meters per second. Okay, so now for part B, we want to find what is the energy lost in the collision. Well, the energy lost, the potential energy of the system doesn't change. The height of the putty and the block don't change. There are no springs. So the energy lost is just the initial kinetic energy, that's how much energy I start with, minus the final kinetic energy. So let's just calculate what this is. K initial equals 1/2 m putty V initial squared. The block isn't moving, so the block initially has no kinetic energy, which is 1/2 of, well, the mass of the putty is 30 grams, but since I want to get an energy in joules, I'm going to convert this to kilograms. So this is 0.03 kilograms times V initial is 20 meters per second squared. If I plug all that into my calculator, I get that this initial kinetic energy is just 6 joules. The final kinetic energy, well, now both the putty and the block are moving with the same velocity. So I can write this as 1/2 m putty V final squared plus 1/2 m block V final squared. This I can also just write as 1/2 m putty plus m block times V final squared. Well, the mass of the putty plus the mass of the block, that's 300 grams. I'm going to write that as 0.3 kilograms times V final, well, that's 2 meters per second. So I multiply this by 2 meters per second squared. Plug that into my calculator, and I get 0.6 joules. So the kinetic energy is 10 times smaller after the collision than it was before. So from this, I find that the energy lost, which is K initial minus K final, this equals 5.4 joules. I start out with 6 joules, I lose 5.4 joules, I'm left with 0.6 joules. It's pretty easy to see that this is 90% of my energy gets lost in this condition, in this collision, I should say. So where does this energy go? Well, some of this energy goes into sound. When the putty smacks into the block, some energy gets carried away as sound. It makes a sound, it goes whack. Some of the energy goes into heat. This little piece of putty is going to heat up a little bit. It goes into thermal energy. But in this case, most of the energy goes into squishing the putty. It actually goes into deforming the putty, changing its shape. That absorbs energy. It takes kinetic energy away and dissipates it. But we don't have to know exactly where the energy goes to know exactly how much energy is lost. We can use conservation of momentum to find the final velocity of the system. And then all we have to do is calculate the initial final kinetic energy. And in this case, if these two things stick together, I will always lose 5.4 joules of kinetic energy, regardless of exactly where that kinetic energy goes. The next example I want to look at is an example of an elastic collision. That is a collision between two objects where the kinetic energy is conserved. So a tennis ball with a small mass, little m, is released on top of a basketball with a larger mass, big M. After the basketball hits the ground, it has a velocity v initial equals 5 meters per second pointing straight up, and the tennis ball has a velocity v initial equals 5 meters per second pointing straight down. After the tennis ball and the basketball collide, what is the velocity of each? Okay, so this is what we're talking about here. I found this video of someone doing this experiment with a tennis ball and a basketball. So you drop them both together, the tennis ball on top of the basketball, and they fall down. The basketball hits the ground here and is going to bounce up. And it's going to hit the ground and bounce up just an instant before the tennis ball hits the top of the basketball. So at this instant between when the basketball hits the ground and bounces up and the tennis ball hits the top of the basketball will be going up and the tennis ball will be going down. And we're going to say they're both going with the same speed, 5 meters per second, but one's going down and one's going up. They bounce, and after they collide, the tennis ball gets launched way up into the air by the basketball. So let's go ahead and use conservation of momentum to solve this problem. First, I'm just going to define the vertical direction as the y direction. So I can say that the tennis ball has an initial velocity, let's call it v naught for the tennis ball, which equals minus 5 meters per second j hat. And the basketball has an initial velocity v naught basketball equals plus 5 meters per second j hat. So this is a one-dimensional collision problem. All of this is happening along the y direction. And we know that this is an elastic collision. So that means we can use our special equation we came up with for elastic collisions. So I can say two things. One, I can say that the initial velocity, or I should say the initial momentum of the basketball plus the initial momentum of the tennis ball equals the final momentum of the basketball plus the final momentum of the tennis ball. Okay. And since this is in one dimension, I'm just going to go ahead and not worry about the fact that these are vectors. I'm going to just leave these all as scalar quantities now. Okay. Now, I also have a special equation that I got for the case of an elastic collision, which is that the initial velocity of the basketball plus the final velocity of the basketball equals the initial velocity of the tennis ball plus the final velocity of the tennis ball. This is true for elastic collisions in one dimension. So this is only true for elastic collisions in one dimension. Otherwise, this equation doesn't hold. But we can use this equation in this special case. Okay. So what I'm going to do is write out, well, what are these, this conservation of momentum equation? Well, we have m times the initial velocity of the basketball. So this is the big mass of the basketball times its initial velocity, plus little m times the initial velocity of the tennis ball equals big M times the final velocity of the basketball plus little m times the final velocity of the basketball. What I'm going to do is go ahead and just divide both sides of this equation by big M. So I get V initial basketball plus little m over big M, oops, make that big, times the initial velocity of the tennis ball equals the final velocity of the basketball plus little m over big M times the final velocity of the tennis ball. Okay, well, here's the thing. I'm assuming that the basketball has a much bigger mass than the tennis ball. Big M is much, much greater than little m. If I make this assumption, then anytime I see this little m over big M quantity, I can assume that that's very small. I can just set that to 0. I'm basically taking the limit as little m gets much smaller than big M, or you can think of this as the limit as big M goes to infinity. So this guy here goes to 0, this guy here goes to 0, and I just get this very simple result, that V initial of the basketball equals V final of the basketball. That is, because the basketball has such a bigger mass than the tennis ball, it doesn't really care what happens in this collision. So I now know the velocity of the basketball. V final of the basketball just equals V initial. It's 5 meters per second. So the basketball keeps going upwards at 5 meters per second. It keeps bouncing as if the tennis ball weren't even there. So now what I want to do is take this result and stick it back into this equation here in order to solve for the final velocity of the tennis ball. Oops, this should be V naught tennis ball plus V final tennis ball. Little mistake there. Okay, I'm going to clean up the screen a little bit and then we'll do that. Okay, so from this conservation of momentum equation and the result that big M is much smaller than little m, the basketball is much more massive than the tennis ball, I get this result. V final of the basketball equals V initial of the basketball. And now I'm going to plug that into this special equation here that I have for 1D elastic collisions. So what I get is V initial of the basketball plus V final of the basketball. Well, that equals V initial of the basketball, because I've taken this and I've plugged it in, boop, right there. This equals V initial of the tennis ball plus V final of the tennis ball. Well, look, I know V initial for the basketball, I know V initial for the tennis ball. I can solve for V final of the tennis ball. V final of the tennis ball equals 2 V initial basketball minus V initial tennis ball. Okay, remember, all of these are velocities along the j hat direction, along the y direction. So this is 2 times V naught b is 5 meters per second, minus V naught t, the initial velocity of the tennis ball, is negative 5 meters per second. This all comes together as 15 meters per second. So the final velocity of the tennis ball is 15 meters per second. This tennis ball, after the collision, goes, shoots way up into the air. The basketball just bounces up at the same speed it would have if the tennis ball weren't there. But the tennis ball shoots way up into the air because it's got this final velocity 15 meters per second. So where does all that extra velocity come from? Well, it turns out that when you have an elastic collision between a very light object and a very massive object, that very light object can actually take a bunch of kinetic energy from the massive object. The tennis ball gains a bunch of kinetic energy from the basketball and goes shooting up into the air. The basketball doesn't mind. It can give up that kinetic energy easily because it's so much more massive than the tennis ball. And this is all just a consequence of conservation of momentum. Initial momentum equals final momentum. And then it's also a consequence of the fact that this is an elastic collision. Kinetic energy is conserved, so I can use this special equation that I derived for 1D elastic collisions. Okay, that's all I'm going to do for now on one-dimensional collisions. In the next video, we'll look at collisions in 2 dimensions. That is, collisions where we have to look at both x and y components of momentum.